Jayakumar Vaidya, and he is the founder and CEO of Anuthantra Private Limited. He also serves as an IBM quantum educator and an IBM Qiskit advocate mentor. He is actively building a quantum community in India and is an IBM certified associate developer in quantum computation using Qiskit. With 15 years of experience in R&D and university level lecturing, he is a senior IEEE member actively participating in IEEE quantum standards. To date, he has published over 15 research papers in international peer-reviewed journals and conference proceedings. Additionally, he has been appointed as a technical paper reviewer for IEEE quantum conferences. He is also a SWAYAM NPTEL portal instructor for the AICTE and DST, which launched India's first undergraduate minor program in quantum technologies. Dr. Jayakumar has conducted over 200 quantum programs, including faculty development programs, Qiskit certification training, and awareness camps across India, USA, Russia, Armenia, Poland, and Malaysia. Sir, over to you.
Thank you, Professor. Thank you for your nice introduction. So, good evening to one and all. Am I audible?
Yes, sir.
Yes, sir.
Fine.
Yes.
So, I try to share my screen. So I'll share this link in the chat box. So who are working with the laptop or computer, please go to this link. Please go to this link. And today we're going to see about introduction to quantum computer. We are about to create a basic quantum circuits. Okay, so this is our given topic today. So I hope every one of you understand what is a quantum computer and how it works. Okay. So even though I want to show some image with you in order to understand how it works. So this is the image. This is the image. You can see how quantum computer appears. So this computer is made up of gold, copper, mercury, whichever material have superconducting property, they will use those material to construct this type of system. Okay. So you can see topmost layer red color. This will cover this entire quantum computer. So this computer does not contain any keyboard, mouse, any monitor. This is entirely new type of architecture what we're going to cover today. Okay. So whatever we're going to discuss in today's lecture, everything we will do in abstract level, circuit level. So those programs are converted and transpiled, and that programs are sent to this quantum computer, and this will run over here. So this is the basic architecture of quantum computer, where you can see layer by layer, okay, where you can see so much of plates. So by each plate, temperature will decrease. So imagine the temperature over here is some 100 degrees Celsius, minus 100. So the next layer will go for minus 150 degrees Celsius. So by reaching the core, so you can see downside over here, my mouse pointer is visible, I hope so. So here it will reach minus 273 degrees Celsius. Okay, so this computer is based upon superconducting quantum computer. So there are so many different architecture of quantum computer. In today's session, we're going to see about how to write a quantum circuit, how to convert into coding form, and how to execute in real-time system. So these are the basic things we're going to cover within this 1.5 hours. Fine. So this is about today's topic. And let me introduce myself. I am founder and CEO of Anutantra Private Limited, and we are offering training, and we are giving workforce for topmost companies, quantum computing companies. And I started my career in IBM Quantum Educator. So before 5 years, I started as IBM Quantum Educator. Then I slowly evolved into IBM Qiskit Advocate Mentor. So before that, I need to clear IBM Certified Associate Developer. So this is the one of the criteria if you want to become Qiskit Advocate. So if you are interested, I will share at end of this session. So to understand quantum computer, we need to understand block sphere. So try to open block sphere. Is my PPT is visible? Empty screen, block sphere with the title.
So the image is not clear, sir. Only the block spin name I can see, sir.
Yes. Because I shared the entire screen, so whatever I change, everything will reflect it immediately. So this is what I want. So I hope qubit is covered in last talk. Whether qubit is covered, quantum bit superposition, it is covered.
Yes, sir.
Okay, good. So consider if you want to visualize any quantum bit, then you need to use block sphere as a tool. So this is a tool. Okay, so this is a tool. Block sphere is a tool to visualize a quantum bit. Okay, so bit stands for binary information. Okay, we try to convert our binary information into a quantum particle. So imagine this is a quantum particle. Okay, quantum particle. So what is the meaning of quantum particle? A subatomic particle. It could be anything, right? So this is the idea of block sphere. It is a tool to represent a quantum bit. Okay, so this sphere is very special because the radius we are going to maintain are equal to 1. So this is called a unit radius. So why we are keeping unit radius? Because we need to maintain a systematic approach. Or we need to use a stabilized approach. Or you can say not comma, you can use slash, a normalized form. I hope everyone know the meaning of the systematic or stabilized or normalized form, because we need to maintain each and everything in a certain order. So what happens if you maintain radius equal to 1? The radius never go below 1 or beyond 1. So this will make your system stabilize. Okay. Next thing, what we do, we try to divide the block sphere into two hemispheres, into two halves. Okay. So what is the purpose of this? Because we need to represent binary information or binary system, you can say, two-level system. So binary is nothing but two-level system. So this is the idea. We are dividing that block sphere into two hemispheres. Okay. Then next, what we about to do, we try to create three Cartesian coordinates, x, y, z. Okay. The first step, we took radius equal to 1. The first step, we took radius equal to 1. radius equal to 1, unit radius. Okay. The next step, what we did, we tried to create two hemisphere. By dividing your sphere. Okay. So why we are dividing into two hemisphere? To implement binary logic. Suppose if you want to implement trinary logic, imagine in such a case, if you want to implement trinary logic, then you need to divide in 3 levels. So this is the beauty of quantum. Okay, so you can increase up to n number of logic by dividing your sphere. Okay, in binary it is not possible. Binary only stays for 2 levels, but in quantum you can increase the level up to n base. Okay, suppose if you are representing n base system, then it will denote QD, quantum digit. So this is most advanced concept where you can reach n number of pieces. So this is ultimate aim of quantum. So for a beginning purpose, we stick to binary logic. If the system is successful, we can extend up to n number of bases. Okay, n number of bases. Then what we are doing, we try to create 3 axes. We try to create 3 axes which is based upon Cartesian coordinates. So 3 axes we're going to use to represent Cartesian coordinates. Because we are using 3-dimensional space. Okay. Taking 2 extremmost point. So these 2 are extremmost point. So this is North Pole. Extremmost point in entire northern hemisphere. Okay. So in same way, we are taking South Pole. So this is the extremmost point in entire southern hemisphere. Are able to follow? I hope so. Right? Then what we are doing after this, we try to map our binary logic. So what is the binary logic? 2-level system. So binary logic is 2-level system. So in block sphere, what we try to do, we try to map this binary logic. So what we are doing, we are mapping binary logic to a quantum particle. So that is why we choose the extremmost point, North Pole and South Pole, to represent 2 different level, opposite level system. Okay. So take an example of binary logic. What we can do? So we can represent any opposite information in binary logic. Take an example of yes or no, true or false. Okay, black or white. Okay, so 0 voltage until +5 voltage. Okay, fully charged or fully discharged. So I can take any 2 system or any 2 information which is extremely opposite in nature. So with the help of binary logic, you can represent any 2 extreme level information. Okay. So these 2 points are called pure states. So if you have pen and paper, please note down all these points with this step-by-step process. So what we did in first, I'll recall from the first slide because you need to follow. So we are using block sphere. We are using block sphere. So we are using block sphere. In block sphere, we are taking radius equal to 1. Okay. Then we are dividing that block sphere into 2 hemisphere to represent binary system or 2-level system. And we are taking 3 axes Cartesian coordinate to represent any 3-dimensional point. Okay. We are taking extreme points in northern hemisphere and southern hemisphere to represent extremely opposite information. Okay. State 0 and state 1. And these 2 points are called pure states. Suppose if you want to use any qubit, if you want to create any qubit, any quantum bit. So what is it possible to create any quantum bit? Either in state 0 or state 1. So these 2 are called states. So remember these points. These 2 are called quantum states. So what type of states? State 0 and state 1? These are pure states. Imagine this is black and this is white. Imagine in such a way. Okay, so only 2 possibility if you want to create any quantum bit. So state 0 or state 1. And this state 0 and state 1 are called known quantum states. So why it is known? Because we try to map binary information. So whatever the classical binary information we have, we try to map this binary information with quantum states. Because of this, we are starting from state 0 or state 1. So next what we do, we take any random point. Inside that sphere, inside this block sphere. Okay. So it will represent quantum particle. This green dot will represent any quantum particle. So this is the logic. Okay. Next what we do, we try to realize what is the position of this quantum particle. So this is in superposition or mixed state. So you can see this point is exactly not in state 0, exactly not in state 1. So it is in between state 0 and 1. So it is in between state 0 and 1. So you can call this point as a mixed state, or you can say in alternative name, which is called superposition. So what is the meaning of superposition? One position over another position. One position over another position. At the same time. So how you can consider this point as a superposition? Because it is the mixture of both state 0 and state 1. So you can imagine it is like gray color. Okay, so this point is exactly black. This point is exactly white, pure white. So if you are mixing these 2 colors, you can have a variety of combination of color. So if you understand this concept, you can understand superposition. So this point is near to stage 0, far away from white. So it will have a dark shade. So dark shade of gray. So if you have any doubt, you can ask now. So any participants having any doubt up to this, you can ask now. Is it clear? Shall we proceed?
Yes, sir.
Yes, sir.
Okay. Okay, thank you, thank you. What we do, we try to create a x dash y dash plane, x dash y dash plane, okay, where this quantum particle exists in your block sphere. Okay, so from this point, what we'll do, we try to project this yellow line from this quantum particle. Okay, so this will exactly intersect with this xy plane. So imagine this is xy plane. This is xy plane. So this will have some intersection. Okay, from this point, so this will have some intersection point. From this intersection point, what you'll do, you'll do projection towards origin. So we'll do one more projection. We will do one more projection from intersection point towards origin. Okay, I will erase all these scribbles so you can understand. So we have electron or any quantum particle in green dot. So what we do, we try to create a vector from origin. So this vector is called quantum state vector. So this vector is called quantum state vector. Okay, with the help of quantum state vector, we can know information about your quantum particle. So this is very, very important. If you want to do any quantum computation. Okay, so without knowing quantum state vector, you don't know the information about your quantum particle. So each and every time we need to monitor, each and every time we need to know what will happen if we are doing anything with your quantum particle. So how will you know? By knowing your quantum state vector. Okay, this quantum state vector will originate from origin and it will point exactly towards the quantum particle. Okay, so this will form a right angle triangle. So if you do two projections, by doing two projections, we can form right angle triangle about 90 degree. Okay, so why we are doing? Because we need to apply trigonometry. So that is why we are doing two projections. With the help of two projections, we are able to get right angle triangle. Once you got right angle triangle, you will get two angles. So this is angle between, this theta is angle between z-axis to quantum state vector. Okay, then one more angle it will generate this psi equal to angle between x-axis to xy projection. Okay, So before this, we have a three-dimensional point in Cartesian coordinate XYZ. After doing all this projection, we try to convert into polar form. Polar form. So this is our ambition. So that is why we took a projection in both direction. By doing projection, we are able to get two angles. With the help of two angles, whatever we are able to describe with XYZ, we are able to describe with theta and psi with the help of two angles. Right? I hope everyone able to understand and follow. Okay. So imagine what is the meaning of theta. So this is the angle generated between your z-axis, their quantum state vector. So remember this. Remember this. And this is your wave equation. So what you call this? This is your wave equation in polar form. In polar form. Okay. So this is your quantum state. This is your quantum state vector. You can say quantum state vector. So this is called psi. Okay. So when angle equal to 0, when angle equal to 0, so recall the previous slide. Recall the previous slide. So this is the angle theta. What happens if theta equal to 0? So the angle is equal to 0. This electron will point to North Pole. The electron exactly located in your North Pole. This is what happened over here. So look at here, when theta equal to 0, this quantum state vector going to point to North Pole, state 0. Okay, so this wave equation, quantum state vector, contains two components. So one is cos, one is sine. These two are opposite in nature. Opposite in nature. So that is why we selected sine theta cos theta, because we want to represent two opposite phenomena. Okay, so cos theta by 2 multiplied with state 0 plus e to the power I psi sine theta by 2 multiplied with state 1. So this I represents complex number. Complex number. Okay, this is your second angle. This is your second angle, and theta is your first angle. So we got two angles in previous slide. Okay, so in this example, we tried to implement only modification in first angle. So focus only on first angle theta. Okay, and this is the linear combination. So this is linear combination, or you can say addition, linear addition. So if you want to describe any quantum state vector, you need to know both components for state 0 and components for state 1. That is why we are adding. If you are adding these two components, you know all information about your quantum particle. So try to understand little by little, then you can have a very good picture of quantum state. Okay, when you apply theta equal to 0, so this will point to North Pole. Okay, so apply mathematically cos theta by 2 multiplied with state 0 plus e to the power psi sine theta 0 by 2 multiplied with state 1, and you will get only sine 0. This entire component becomes 0, so everything will cancel out. You will only get 1 into state 0, so you'll get only state 0. So this is equivalent to identity gate. Identity gate. So it will do nothing. It will do nothing. So if you apply theta equal to 0 for any quantum state, if you apply theta equal to 0 for any quantum state, so what happens? It will do nothing. It will do nothing. So the state remains same. State remains same. So it is like a pause button. Suppose if you want to do nothing with your quantum state, then you can use this technique, apply data equal to 0. Okay. So if you have any doubt, you can put in chat box. Is it clear? Shall we move?
Yes, sir. Yes, sir.
Okay, thank you. Thank you. So next, look over here. We try to change d equal to pi. Imagine if you apply d equal to pi, what happens? Apply in this formula. Okay. So cos pi by 2 multiplied with stage 0 plus e to the power psi sin pi by 2 multiplied with state 1. So here this cos component becomes 0. So 0 into stage 0, the whole component will get cancelled out. It will remain only sin pi by 2. So sin pi by 2 will get 1. 1 into state 1, you will get state 1. Okay, so this is mathematical form. What happens if you apply d equal to pi? Your quantum state will convert it into state 1. Okay, so imagine the quantum state in state 0. If you apply d equal to pi, it will convert into state 1. So this is nothing but NOT gate operation, which is nothing but inverse or opposite or negotiation. Okay, so all these meanings are synonymous. Okay, if you want to look visually, if you apply d equal to pi, your quantum state will change from state 0 to state 1. Your quantum state will convert from state 0 to state 1. So this is a NOT gate operation or negotiation operation or inverse operation. So in multiple words you can say. Suppose if your quantum state is state 1 already, if you are applying d equal to pi again to this, then your answer will be state 0. Okay. So it is about your quantum state where we are applying. So in this example, we started from 0. From 0, if you apply d equal to pi, it will come to state 1. From state 1, if you are applying again d equal to pi, it will go back to state 0. So we covered two examples. One example is d equal to 0. If you apply d equal to 0, nothing will happen, which is equivalent to identity gate. If you apply d equal to pi, it will do NOT operation or negotiation. Okay, we covered two gates, and this is about third gate. This is about third gate. So look, the angle pi d equal to pi by 2. So if you apply d equal to pi by 2, you will end up with cos pi by 4, sin pi by 4, and your quantum state will become state 0 plus state 1 by root 2. So you can rewrite this formula 1 over root 2 multiplied with state 0 plus state 1 in this way. So what it means, if you apply d equal to pi, it will go half of the way. Exactly in the equator, it will reside. Okay, in equator, exactly in the x-axis. X-axis. So that is why you have both components of state 0 and you have both components of state 1, and it is in between, exactly in the equator. Okay, so exactly in the equator means it is equal superposition. Equal superposition. So anywhere in your equator, what you need to say, supposed to say, it is in equal superposition. So this special gate is called Hadamard gate. Hadamard gate. So note down this gate. When you apply delta equal to pi by 2, it will exactly create transition from 0 to equator. 0 to equator. Okay. The next gate is, if you apply delta equal to pi, it will go to x-axis, which is nothing but positive state. Which is nothing but positive state. Because x-axis is real axis. Okay. So opposite side will have negative x-axis. X-axis. In short form, you are representing negative state. So we have state 0, state 1, along with we have x-axis, positive state, negative state. In same way, if you apply the second angle pi by 2, what happens? It will convert the real component into imaginary component. So y-axis is about imaginary axis. That is why the I will act over here. So you can say negative y-axis. How will you represent negative I quantum state? Okay, this rotation is about pi by 2. So if you apply psi equal to pi by 2, it will move your quantum state from x-axis to y-axis. So you can look over here. Now the imaginary value will take part in your state 1. So this is how, if you apply the second angle pi by 2. So we covered 3 gates. Okay, quickly I will try to refresh. The first gate is identity gate. If you apply delta equal to 0, it is identity gate. So next what we did, we tried to apply delta equal to pi. If you apply delta equal to pi for first angle, it will create a NOT operation. Okay. Then what we do, if you apply delta equal to pi by 2, it will create equal superposition, Hadamard gate. If you apply psi equal to pi by 2 second angle, then what it will do, it will convert any real component into imaginary component. That is about state I plus I. Now we got axillary axis. So remember, so we have state 0, state 1 along with the x-axis, positive state and negative state. Along with this, we'll get y-axis. So we have 3 pairs of quantum basis. Quantum basis. So any doubt until this? Any doubt?
No, sir. No, sir.
Okay. Yes, it is negotiation. Angle need to be considered. Yes. Okay, fine. So next what we do, we try to look the same concept with the help of matrix. The help of matrix. So this is matrix. So this is column matrix. So this is column matrix. So look, stage 0, where it is existing in northern hemisphere. Northern hemisphere. Okay. So imagine this matrix into 2 hemispheres. So this is northern. So this is southern. This is southern. Okay. So where stage 0 exists in northern hemisphere. So that is why we are denoting 1. 1 means yes, you can consider yes to represent stage 0. So there is no relevant of state 1 in this quantum vector. So that is why we represent 0 for southern hemisphere. Okay. So we try to map the physical quantity in a mathematical abstract way. Okay. So look at the second example, state 1, which is opposite of state 0. Opposite. So where state 0, sorry, this is keep on coming. Opposite of state 0 and state 1. Okay, look, the upper component is 1 over here. The lower component is 0. So here it is reverse. It is reverse. The upper component is 0 and lower component is 1. So these two are opposite in nature. Mathematically, you can say orthogonal to each other. In two-dimensional, you can represent with 90 degree. In two-dimensional, you can represent with 90 degree. Okay, so next you can see positive state. So where positive state exists, exactly in the equator. Exactly in the equator. So it is equal superposition. Equal superposition. So what is the relationship between positive state with respect to state 0 and respect to state 1? The both components are existing. The both components are existing. That is why the upper component also 1, the lower component also 1 to represent the location of positive state. And this is amplitude. This is amplitude of this signal. Okay. So why there is no amplitude for state 0? Because it is exactly in state 0. State 1, it is exactly in state 1. So you can consider 1 as the amplitude. But in case of positive, it is exactly in between state 0 and state 1. That is only half of the amplitude value. Okay, so this is the abstract way. So if you want to represent negative state minus x-axis, then you need to represent with negative sign, because it is in opposite side of that sphere, opposite side of block sphere. So that is why you got negative component for negative sign for second component. So imagine this whole area for positive 1. Okay, the opposite side of this sphere represents negative state 1. Negative state 1. Okay, so if you understand state 0, you can understand state 1. If you understand these both, you can understand positive state. If you understand positive state, you can easily able to recognize negative state. Why there is negative sign for second component. Okay, so next look at the y-axis. So this is your y-axis. So y-axis represents imaginary value. This whole y-axis represents imaginary value or imaginary component. Whole x-axis contains a real component, real value. So this is the difference between x and y. Okay, so y dealing with imaginary, that is why the second component is I. That is why the second component is I. Look at the minus I, opposite side of y-axis. The negative component sign is negative. So the second component of minus I is negative. So which indicates these two are opposite in nature. These two are opposite in nature. These two are opposite in nature. If you have 3 pairs, you can represent any point in your block sphere. So you can represent any point in your block sphere. Okay. So I'll share this link with you. I'll share this link with you. Please go and Imaginary value you can consider in mathematics. One is real part, one is imaginary part. You will consider the real value only. But what is the importance of imaginary? If two imaginary components are colliding with each other, it will turn into real value. Okay. So take an example of I square. I can use open board. Okay, so take an example of any quantum state. Any quantum state. So quantum state can be represented in the form of complex number. Complex number. So what is the form of complex number? A plus I B. Okay, so where A and B are real values. Real values. Okay, so I is imaginary. I is imaginary. So you can consider x and y axis in this way, where x axis is real, it will represent real value. Okay, y axis will represent imaginary value. Imaginary value. Suppose if you are pointing any value, it is the combination of both real part, comma, imaginary part. Okay, when two imaginary value are colliding with each other or reacting with each other, take an example of I. So what is the value of I? It is equal to root minus 1. What is the meaning of I square? So I into I. So if you are doing I into I, you'll get minus 1. So minus 1 is real value. So in mathematics, only we will consider real value if you are try to solve your equations. So if you are getting any imaginary value, you will discard. Okay, why you are discarding? Because it is an imaginary value. Okay, so we are doing calculation until if two imaginary value are colliding with each other or reacting with each other or multiplying with each other, it will cancel out. I hope this will help you to understand. So if you want to represent quantum state, you need to represent with the help of, right? So how to, yes, undo. Okay, if you want to represent any quantum state, you need to represent in the form of complex number. So that is why we are using real and imaginary component. Is that clear? Junaram, is that clear? Hello? Just message. Okay, thank you. So all of you go to this link. Why it is writing? Okay, here it is. So go to this link, and you can play all these gates with you. So we covered stage 0, stage 1. So these are pure states. So these are called pure states. So if you want to create any quantum bit, you need to start from pure states. Initial state. So you can say initial state. If you want to create, if you creating any qubit, either it will start from zero.
How much you learn from theory, from practice, from mistakes? Either. Maybe how much you learn from theory, from practice, from mistakes. How much you learn?
Ma'am, somebody is speaking. Okay, thank
আমি
you.
তোর পাশে পাহারাদারের মতো বসে থাকলে তুই ভালো পড়িস কেন রে?
Hello, ma'am. Somebody is talking, please. No.
How
Okay, thank
am I good at it? আমি তো কোনো কথা বলবো না, কিছু বলবো না তাহলে।
Can anybody check who is speaking? Otherwise, I can put mute for all. Okay, thank you.
Sir, voice is mute. I think the voice is not coming. Sir, not audible. Sir, voice not audible.
Now audible, sir? Now audible?
Yes, sir. Yes, sir.
Okay, okay, thank you, thank you. Because I put mute for all, I forgot to unmute myself. Okay, once again, I will repeat, no issue. So this is very basic and fundamental. I hope all of you able to go to this link. So go to this link and practice yourself. Practice yourself. So these two gates are pure states. These two states are pure states. If you are creating qubit, either you need to create in state 0 or state 1 by default. Okay. So why we are creating in state 0 and state 1? Because these are known quantum states. Known quantum states to us. So that is why we are creating. Okay. So next what we do, we try to apply NOT gate from stage 0. So click stage 0, click stage 0, click X gate. So X gate stands for NOT gate. X gate stands for NOT gate. NOT gate. Okay. Imagine if you are in stage 0, if you apply X gate, it will turn into state 1. From state 1, if you are applying X gate, it will turn into stage 0. So if we apply 2 X gate next to next, which will cancel each other. Which will cancel each other. So I will repeat. Okay, click stage 0, click X gate, it will turn into state 1. So look at here. Again from state 1, if you are clicking X again, it will go back to stage 0. So applying 2 X gate will cancel each other. Okay, fine. So click 0, click Y gate. What happens? It will come to state 1. But you can see there is a change in phase pi by 2. So it will introduce phase shift. So it will do X operation or not operation along with pi by 2 phase flip. Phase flip. So this will have some advantage when compared to X gate, where X gate will not indicate these changes. So these changes only possible by Y gate. So in classical, you cannot have these type of changes. Okay, only not operation you will get. Okay, from state 1, apply y again, it will go back to stage 0. It will go back to stage 0. Okay, so next important gate we need to discuss about Hadamard gate, H gate. So H gate stands for Hadamard gate. Hadamard gate. So Hadamard gate is very important. It will create equal superposition. Equal superposition. So from stage 0, it will come to x-axis exactly in positive state. So you can see downside, this amplitude is exactly half. Exactly half. Okay. So from here, if you are applying Hadamard gate again, it will go back to stage 0. From positive state, if you are applying Hadamard gate, it will go back to stage 0. Okay. So I will discuss in pen. So we are in stage 0. If you are applying Hadamard gate, it will go to positive state, exactly in the equator. Okay. So remember this. Remember this. Okay. So from state 1, click state 1, apply Hadamard gate, it will go back to negative state. So from stage 0, if you apply Hadamard gate, it will go to positive state. From positive state, if you apply Hadamard, it will go back to stage 0. Okay, in same way, if you are in state 1, if you apply Hadamard gate, it will go to negative state. From negative state, if we apply Hadamard, it will go back to state 1. Now we can recheck with this action. So now we are in negative state. Apply Hadamard, it will go back to state 1. So from state 1, apply Hadamard, negative state. From negative, apply Hadamard, it will come to state 1. So we try to do this circuit. We try to do this circuit with the help of IBM login. Okay. So if you don't have login, so try to create this login. So look at the chat box. Look at the chat box. I will share once again. I'll share once again. So all of you go to this website. Okay, try to create a login. If you are not able to create a login, what you will do? You will do after this session. So once you logged in, you can see dashboard like this. Okay, so this is a IDE. So this software is called Qiskit. So Qiskit is developed by IBM. Okay, so Qiskit stands for Quantum Information Science Toolkit. So this is the acronym for Qiskit. So this is the framework where you can do simulation, quantum simulation plus real quantum execution. So you can do any quantum experiment in two ways, either by simulation or either by real quantum execution. So this is called composer. So what I am showing, it is called composer. So how to reach composer? I will quiet this board. So how to reach composer? So go to your login. So downside you can see composer link. So click start building. Okay, so otherwise you can chat in this way. Google for IBM Quantum Composer. So after login, Google for IBM Quantum Composer. So directly you can lead to this page. So without login also, you search IBM Quantum Composer, it will lead to this page. So here you can notice 4 quantum bits Q0, Q1, Q2, Q3. Okay. So for simplicity, we try to delete all qubits except one. So click Q1, select delete button. So select Q1, click Q1, select delete qubit. Q1, select delete qubit. So do for C4, select minus, select minus, select minus. So keep only one quantum bit, one classical bit. So for your convenience, I will zoom. So Q stands for quantum, C stands for classical. So you can see the difference over here. Whether my screen is zoomed, are you able to see the magnified version?
Yes, sir. Yes, sir.
Okay, okay. So you can see quantum. So you can see only single line, but classical you can see double line. So you can see all quantum bits individually, but combined view of classical bit. So for an example, if I click one more qubit, so I have individual view. Okay, if I have one more classical bit, so I have only double line. So always classical you can see as a double line view, but quantum as individual line. So this is one more difference. Okay, so all qubits started from stage 0. So this is stage 0, this is stage 0, because these two are known states. The circuit is empty. So here you can see wires. So this is your wire, like classical wire. Imagine like a classical electrical wire. Okay, so there is no power supply. So what you can consider stage 0 as off state. Off state. So off state means no power. No power. Okay. So look at Qisphere. So to change this environment, what you can do, go to view, go to panels. Okay. Go to view, go to panels, enable Qisphere. So you disable all these panels. I disable all these panels except Qisphere. So our circuit is empty. Now where it is pointing? It is pointing to North Pole. It is pointing to North Pole. Wait a second, graphical editor. Yes, so we have 2 qubits. Sorry for that. So select only one qubit, one classical bit for easier understanding. So we have only one quantum bit. One quantum bit contains 2 quantum states. So for one qubit, we have 2 quantum base states. Base states. So which is nothing but stage 0 and state 1. Our circuit is empty. That is why it is pointing to stage 0. Our single qubit is empty. That is why it is pointing to stage 0, North Pole. Okay. Then what you do? You can observe over here. This is called phase disk. So move your mouse over here. So top right corner, you can see phase disk, which is in gray color. So I can zoom for your convenience. So look over here. Look over here. Here you can see a phase disk. So real component equal to 0, imaginary component equal to 0, probability of state 1 is 0% because it is in stage 0. It is in stage 0. Now what you can do, you can apply NOT gate. We already covered in block sphere, right? We already covered. So stage 0, you implemented NOT gate in Qisphere. Then what happens? Power supply will happen. Power supply will happen, and this is state 1. If this is off state, and this will consider like on state. So opposite. So imagine you have a phase disk. Imagine you have a phase disk where you can see changes over here. Now your disk is turned into blue color. What is the probability of state 1? Now it is showing 100%. So this is how you can play with this Qiskit to do any changes. Okay. So if you're implementing one more NOT gate, what happens? So recall from previous topics, stage 0, then this is NOT gate 1. So this will change your quantum state into state 1. Okay. Again, if you're implementing NOT gate 2, again it will change from state 1 to state 0. So applying 2 NOT gate will cancel each other, which will go back to original state. Original state. So this is very easy. Now we can see the changes in your block sphere. So before that I will delete. Before that I will delete one NOT gate. One NOT gate. So you can see changes over here. Now it is pointing to south pole because we implemented one NOT gate. So from stage 0, if you are implementing one NOT gate, it will pointing to south pole. Okay, I hope this is clear for each and every one. Okay, so the next important gate, Hadamard gate. So this H gate stands for Hadamard gate. So in theory session, we covered about Hadamard gate. So what is the equation for Hadamard gate? 1 over root 2 multiplied with stage 0 plus state 1. Okay. So this will create equal superposition in the equator. So what it means? It will point both North Pole and South Pole simultaneously. So you can see over here. So this is equal superposition. So simultaneously, the same quantum particle is pointed to both North Pole and South Pole. So if you are not able to understand this, you can able to understand this half circle. So this is half filled. So 50% for stage 0, 50% for state 1. So this will create equal superposition. So imagine like this. Imagine like this. Okay. So what happens if you implement one more Hadamard gate? It will cancel each other. It will go back to original superposition, sorry, quantum state. So we started from stage 0. So we implemented Hadamard 1. It will go to positive state, equal superposition. Again, we are applying Hadamard gate 2, which will go back to stage 0. So I will denote in this way, stage 0, Hadamard gate, it will go to positive state. Again, if you are applying Hadamard, it will go back to stage 0, original state. So applying 2 Hadamard gate will cancel each other. Okay, so this is how you can understand all these gates one by one. Okay, so if you want to see the code, you can go to view, you can go to panels, you can enable code editor. So you can see equivalent code in Qiskit. Equivalent code. Why it is not coming? Okay, coming. Okay, what I will do, I will disable all. Yes. Now you can see the circuit is empty. The circuit is empty. Okay, we have empty circuit. So we have empty circuit. So you can change over here Qiskit. So this is your Python code. So change your code into Qiskit. So this will enable Python code. So we created 2 register, 1 quantum register, 1 classical register. We tried to create quantum circuit. Our circuit is empty. Our circuit is empty. Okay. So what we do, we try to implement one NOT gate over here. We try to implement NOT gate. So we implemented NOT gate in Q0 and you can see changes over here. So this is our circuit. In circuit, we are implementing NOT gate with the help of X, and where we are implementing Q register 0. So that is why we got equivalent code for your circuit. Okay. So what do you do? Try to implement a Hadamard gate in Q0. So next to NOT gate, and you can see changes over here. So here Hadamard gate, where you are implementing quantum register 0. Okay. In same way, you try to create one more qubit. So click plus. Now you can see changes in your quantum register. Now quantity become 2, classical quantity become 1. So in same way, you can create one more classical bit. Now both quantum and classical become equal to 2. So this is how you can learn from this composer. So composer is very, very easy if you want to learn graphically. Okay, it will generate equivalent Qiskit Python code for you. Right, we covered NOT gate, then we covered Hadamard gate, then we covered S gate. Okay, we covered S gate. I will show how S gate will work. So S gate will create pi by 2 phase rotation. Pi by 2 phase rotation. Okay, so you can see S gate effect with the help of Q sphere. So you can see color change. So color is pi by 2. You can see this pink color. So that is why it is having pink color. I try to delete one quantum bit. Now you can see phase change. So we have NOT gate followed by S gate. S gate will introduce pi by 2 phase shift. So you can enable phase angle. So if you enable phase angle in your Q sphere, you can notice what is the angle given over there. I try to move this away. Yes. So you can see phase angle also. Okay. So what you do, try to delete this S gate. You apply only the NOT gate. So click this gate, press delete button. Simple. And you can see no phase change. So move your mouse over here. Phase angle is 0. So with this, I will stop over here. I will open for the question. So thanks for patiently listening to this lecture, even though this is very short time. I try to give a glimpse about Blocksphere, a glimpse about IBM Qiskit platform. Okay. So if you have doubt, please go through this video again and again. So already recorded, organizer recorded. So if you have any doubt, you can contact me. You can post your questions over here. And if you want to communicate with me, you can communicate with my social media ID. So this is my ID. If you want to learn quantum, you need to learn very slowly. Otherwise, you will get more and more confusion easily in quantum. So this is my ID. Thank you, ma'am. Thanks for all the participants patiently attending even after evening. Very difficult for every one of us.
Many thanks for your insightful session, sir.
Thank
Very
you, ma'am.
wonderful session.
Thank you.
We look forward to learning more from you in tomorrow's session.
Definitely, definitely. I will continue the same flow.
Now the session is open for interaction. Participant, if you have any doubts and queries, please raise. points. Any question? Any question from participants side?
I think it will take some time to grasp. Maybe tomorrow they will shoot.
Yes, I think so. I think so, sir.
Yes,
So it is dinner time now. So
Yes,
we are now closing the session. Tomorrow at 6 p.m. we will again learn from you.
Thank you. Thank you.
Thank you so much. Good night, participants.